Okay, in this example, we're going to look at the standing wave pattern that's created on a string that's fixed at both ends. So if we imagine it's tied down at both ends, and what that means is I need a node at both ends. It says the speed of sound on the string is 380 meters per second, has a length of 50 centimeters, or 0.5 meters. And it says determine the fundamental frequency, the first and second overtones. So for the fundamental frequency, we're going to do the n equals 1 pattern. For the first overtone, that'll be the n equals 2. And then for the second overtone, don't overthink it, n equals 3. Okay? So the n equals 1 pattern is the simplest pattern possible. If we need a node at both ends, that means it's going to go up and come down one time. And that means that the length of this string is equal to 1/2 of a wavelength. If we recall, the general formula for a string that's fixed on either end is n equals lambda over 2. And so here you can see that we've put 1 in for n. In that case, my length is 0.5 meters. My wavelength works out to 1.0 meters. And then since I have the speed of sound on that string, I can use the universal wave equation to come up with the frequency. So I have a speed of 380 meters per second. Don't know my frequency. I have a wavelength of 1.0 meters, and so my frequency just works out to 380 hertz in this case. For the n equals 2 pattern, again, this is like my second simplest possible thing. Here, instead of just going up and down once, I go up, I go down, I come back up. That is the second simplest way to get a node on either end. Here I can see that my length is equal to my wavelength directly. If I wanted to think about it as having used the formula, I would have said that my length is equal to 2 lambda over 2, and you can see that I just simplified 2 over 2 to lambda. Again, the length of my string is fixed, so it's 0.5 meters, and that's going to be equal to my wavelength directly. And using the universal wave equation, here I'm going to get a frequency of 760 hertz. And finally, in the n equals 3, or the second overtone, again, if the standing wave is going to reflect in such a way that each time the reflected wave bounces back and forth, it lines up constructively or in phase with previous waves, that means I need nodes on the endpoints. Simplest, second simplest. The third simplest way to do that kind of looks like this. And what we can see here is we have 1 and another 1/2 of a wavelength. So our length is equal to 3/2 of our wavelength. If I imagine the general formula, L equals n lambda over 2, then L would be 3 lambda over 2 here because we're talking about the n equals 3 version of the wave. Putting in my length, I can see that the corresponding wavelength to this is 0.33333 meters. Finally, using that just keeps going, but whatever. V equals F lambda, or the universal wave equation. Speed is 380 meters per second. F 0.333 meters, so on. And my F is going to work out to here 1,100 740 hertz. So if you plucked this string, the main frequency that you would observe is a 380 hertz frequency. But if you had an oscilloscope or some other complex device that would be able to measure the other frequencies produced by this, the 760 hertz would be the second strongest thing that you'd hear, although it would be quite a bit quieter. And 1140 hertz would be there too. There'd be more higher order frequencies associated with the higher order standing waves, but those are the main three that you'd observe.